Okay, so as you can see, the title is Picturing Even More Quantum Processes. I'm picking up from Bob's talks in the morning. And in the next hour, what I'm going to do is review what he said. I might say some things in slightly different ways. But again, just to revisit a lot of the same principles. Well, what he talked about in the morning and the afternoon was really having to do with general principles about boxes. And we dealt a lot with black boxes and how they would connect to each other and sort of quite abstractly. But what this talk is about is really about filling in the boxes. It's about using these spiders, these phases, to construct things, to build stuff. And to exhibit some of the tools that we have for proving things about the maps that we build. So we're going to enrich the language to do that. Along the way, we'll define complementarity, so we'll define what it means for two bases or two measurements to be complementary to each other, which plays a big role in quantum theory. And also strong complementarity, which is less of a standard thing. I think we kind of cooked it up, but it's quite a natural concept, and that plays a big role in the ZX calculus, which is our main. I say it's kind of a Swiss Army knife for calculating quantum things. So you can use it for lots of different kinds of calculations, particularly calculations about things involving qubits. So that's where we'll finish today. And then carry on. My second hour will be more about applications. So this is more of a tool kind of talk. So this, in Bob's second hour, we talked about quantum states. They were these doubled things. They look like this. That's just a quantum state row. And they can always be written in terms of a pure state, so one of these purely doubled things, and discarding. Or equivalently, the transpose of discarding, which is this maximally mixed state. So I can always write a state like that. So up to bending a wire, quantum states are really just positive maps or positive operators. So you see here, this is just an F dagger F. So that's like a density matrix row, which is just kind of bent around, right? So there's nothing really mysterious about these bold things. It's really just a bend to the wire. Quantum maps look like this. They can always be purified, as Bob said. And I'm not sure if he mentioned this, but there's an alternative way we can write this trace, this discarding map, as a sum across some orthonormal basis. Which gives us, in addition to this kind of Stein-Spring purified form, also gives us a Krauss form. So we could write any of these maps as a sum of its pure components, which you should think of these things as like Krauss operators, Krauss matrices. So a quantum map, again, just up to a bend to the wire, is something familiar if you're familiar with quantum theory. It's really just taking a Krauss representation of some CP map and sort of twisting things around a bit. So I guess the point I was trying to make is that these aren't kind of so far from the standard things. It's just we've done it in a way that's more convenient for this process theory point of view. And as Bob said, the physically realizable maps satisfy this causality postulate. And if we look at this applied to a state, this just amounts to taking a trace of the thing. So it's kind of like the norm of the state. So the causal states are density matrices. They're positive operators, the traced one. The causal maps are CPTPs, so just the sort of standard thing, the general way you would model a quantum revolution. Right? Classical states look like this. They could always be written like this. As a pure state, followed by one of these bastard spiders, which corresponds to a basis measurement. hence that notation of putting the little dot there. Now, the point of putting the dot there is it sort of singles out a preferred basis. So unlike the quantum, the double wire, classical wires have a type on them, and that type is given by the color of that dot. And the preferred basis is important because it tells you how a classical state is a probability distribution. It says that if I take this thing, which in particular is a vector, and I expand it with coefficients in that basis, so white basis vectors, white dot, these things are all positive. So I should think of all of these coefficients as probabilities, right? So I think of my classical states just as probability distributions. And then causality, my causal classical states force these things to sum up to 1. So really genuine probability distributions. So the causal classical states are just probability distributions. The causal classical maps are the linear maps, which preserve probability distributions, so stochastic maps. So the way we've set things up is that these quantum classical maps that Bob talked about simultaneously generalize familiar quantum operations as well as stochastic maps. So you can define a lot of this stuff using bases and sums, and that's the normal way to do it. But there's a much more elegant way to do this when working with pictures, and it just sounds cooler because it's spiders. So spiders are the main tool I'll be using for defining and proving all sorts of stuff for the next 2 lectures. You should think about these things as generalized correlators. There's something that forces all the legs to be the same. Bob defined a bunch of special cases of these things, the copy, the fuse, and all that sort of stuff. And they have classical versions, and they also have quantum versions. The classical versions can really be thought of as classical stochastic operations. So for instance, this one is actually just preparing a probability distribution in perfect correlation. So just a pair of classical systems that are perfectly correlated. These, at the moment, might seem a bit more mysterious. In particular because not all of them are necessarily causal. But I'll come back to that. These things you use to build actual quantum maps, right? So that's but both of these will play a role, as well as the bastard spiders will come up quite a bit. In particular, this special one, this measurement spider. Right, so that's kind of the end of what Bob has said so far. And this is the new stuff. So, as most of you know, most interesting quantum stuff comes from not looking at a single classical context in your quantum state space, but looking at how multiple classical contexts interact with each other, multiple measurements. The way we do that is we just introduce new bases. And notationally, we do this by introducing new colors of spiders. So you could think of this white spider as being the spider which represents the computational basis. And this gray spider is the spider which represents the plus basis. Right, so now we have 2 bases around, and we're going to look at how these spiders interact with each other to explain various aspects of how these 2 contexts interact with each other. So, in particular, each of these spiders induces a basis measurement. So we have a quantum system coming in both cases. Here, we're going to measure with respect to this orthonormal basis, the computational basis. And we'll get a probability distribution for each of my outcomes in the computational basis. And that probability distribution is encoded in the white basis, right? So there we have a classical wire, which is sort of colored white, because that's how the probability distribution is encoded. In the gray measurement, we measure in the gray basis, which you could think of as, say, the plus basis. and probabilities are encoded in the plus basis. You can think of this. Well, I'm kind of two minds about this. You can think of this maybe as just some bureaucracy that you have to remember which basis these things were encoded in. But maybe this is also useful information as well. Maybe I've measured two drastically different observables, and this could be something like this color could tell me what kind of quantity I have, and I need to do something non-trivial to change one kind of quantity to another kind. But mathematically, we could just do everything in one basis, which means we would have a bit of ugliness. We'd have to do something else here, right, to get everything uniform. It turns out a lot of things are just much more elegant this way to allow different colors of classical letters. The adjoints of these things are preparations, what Bob called encodings. So we take some classical data as our input, and we condition what we prepare, what quantum state we prepare on the classical data we got as input. So if we get classical state 0 in, we prepare something in a, say, a spin-up state, and if we get 0, we prepare in a spin-down state, something like that. Right? And we can do this for both bases as well. So what happens when we measure and then prepare? Well, you can compute this. It's pretty easy to do. So this row is just an arbitrary quantum state coming in. It's got some coefficients here. And what happens when we measure it and then prepare it is all of the off-diagonal coefficients get killed. See, I've got an ij there. I've just got ii here. So that's just decoherence. It's sort of, you wouldn't see it side by side, but this is like projecting to the diagonal of a density matrix, so the normal kind of decoherence map. But then decoherence models, generally you would think of it as bad, right? It models the situation where this state has unwittingly gotten measured by the surrounding. We don't know what that outcome was, right? But we could just as well think of this thing as a measurement. Now we have access to this classical data, and we want to hold on to it, right? So the way we do that is we keep a copy, right? So I'm going to copy out that classical data, and then, well, my system's still there, so I can visualize this as just preparing again, right? Well, that's one way to think about it. You could also think of this as just some kind of non-demolition measurement, right? So something has happened to my system. It's obviously been projected somehow, but also I have some classical data coming out. Right, so general non-demolition basis measurement can be pictured that way. And in fact, we get our usual measurement just by taking one of these non-demolition things and then throwing our quantum state in the trash, right? And that's just the usual demolition measurement. So what happens when we prepare and then measure? Well, it depends on which bases we choose. So one extreme is that if we prepare, if we encode in one basis and then we measure again in the same basis, well, we should just get the bit we encoded back out. That's kind of standard. The other extreme is if we prepare in one basis and then we measure in another basis. So if they're the same, it could be like this, but if they're somehow drastically different, then we could actually get no data related to this input, right? So I've prepared something, or I've encoded something, and then I've measured it, and I've actually got no classical data flow from my input to my output. Yeah, in other words, no data transfer, right? This is precisely what it means for two measurements to be complementary, right? So if I prepare in one, say, classical context, and then I measure in another one that's complementary, I have no information about what preparation I did in that other basis. This is precisely what complementary observables are. And you can already see this picture coming up in quantum protocols, which I'll talk about a bit more next time. But at the kind of heart of quantum key distribution is, well, I want to send some bit to Bob, and then he has to guess which basis I encoded that bit in, right? So it's usually a plus basis or a zero basis. And in one situation, he'll guess right and he'll be happy. It took me a while to find a picture of Bob looking happy, but I did find one.
This is Barbados. How could I be happy?
Yeah. But then if he chooses wrong, as you can see, Bob is back to his usual self here. So you see complementarity playing a big role in lots of protocols. And you can also see in this kind of Stern-Gerlach type setup, where, say, I'm doing, well, there's a lot of variations you can imagine, but this one where I'm doing 3 measurements in a row, a z, an x, and a z. And then by complementarity, all of these intermediate bold parts are just going to fall away, you see? So that's, these bits of wires have gone away just because of the complementarity rule, right? And the classical output, the output of my third measurement, which has ended up here, this wire, as you can see, it has no relationship to any of these other two. I mean, there's just no connection there. And that's come from the complementarity rule. Which, well, the other way you can say this is my third output is uniformly random. So the white dot here is like the classical analog of the maximum mixed state. It's just a flat probability distribution. And in fact, it stays random even when I post-select my first measurement to be, say, spin up. Right? So this is the normal kind of Stern-Gerlach setup, is I block off my spin down on my first device. Right? So I should only be getting spin ups out. So I should get spin up out of my third measurement. But this shows that it's still uniformly random. Like, ooh, weird quantum stuff happening. But it follows just immediately from this diagrammatic rule. So that was a couple of operational kind of consequences you could see of this complementarity rule. Mathematically, complementarity really just means these two bases are mutually unbiased. So 2 bases are mutually unbiased. The more familiar equation is probably this one, that the modulus of their inner product is 1 over root d. We can also give a doubled version, which is just a bit more convenient of how we do our calculations. Right? Then 2 bases are mutually unbiased if and only if they satisfy the complementarity equation. So here I've given the doubled version of the equation and also kind of the unfolded version. And this is very easy to prove. So in one direction, we just look at the inner product. Well, let's see. Yeah, I put the scalar back in this equation, which I ignored before. So I look at the inner product, this part, what if I, here. Yes. So this J being measured here will end up with a quantum post-selection, right? Well, this I being encoded will be a quantum I, right? And that's just the adjoint of that. Then I apply complementarity. Then this thing deletes that, so it sends this part to 1. This thing deletes that, so it sends that part to 1. The inner product is 1 over d. That's just how it goes. The converse, we just look at the matrix entries of the right-hand side and the left-hand side. So again, we can just put these white and gray points around, and these 2 maps have to be equal just by the complementarity law. So there's actually a slightly nicer way to say this. I did that concretely to get most quickly the standard definition. So we can say when an arbitrary state is unbiased with respect to a basis, and it's pretty much the same thing, that if I take the inner product of this state, psi, with any basis element, it equals some fixed scalar lambda, where it doesn't depend on I. And of course, whenever this thing is normalized, that has to be 1 over d. That's the same thing as saying that I've got a state psi, and when I do a measurement in this gray basis, I don't get any information out of it, so I get a flat probability distribution. That's what it means for, kind of operationally, what it means for a state to be unbiased with respect to a basis. Then, it's very quick that this is equivalent to the complementarity equation. You just roll through it in both directions. So the unbiased states, we can always represent them by d minus 1 complex phase factors. So if you think about what kinds of states are unbiased with respect to a basis, thinking of the vector, all of these things will be just complex phases, right? So we can eliminate the first one. We can make the first coefficient 1 just by multiplying by a global phase, and then we get these other phases. So actually this alpha here is a list of alpha j's, and the same. So this is a white phase with respect to the white basis, a gray phase with respect to the gray basis. So we define these phase points to give us a bit more richness in the language, or phase states. Specializing to the 2D case, the phase states look like this. Right? This is the phase states for the computational basis and for the plus basis. And on the block sphere, these just live on the equator. So you can see, because the decoherence map takes something on the surface of the block sphere and projects it onto the center axis, that if we project anything from the equator onto the center axis, we'll just get the maximally mixed state. So this is saying that the decoherence phases get clobbered when we go from quantum to classical. So decoherence kills phase data. So that's how you define phase states, but we also want to define phase maps, so rotations of the block sphere. And how we do this, well, a clue comes from this group structure, which any of these spiders will define. So you saw from Chris's talk that you can think of the part of this Frobenius algebra, the part of this spider with 2 legs in and 1 leg out as a sort of multiplication. If we take this a bit more seriously, we can think of this thing as a multiplication of phases, right? So I put a phase in there, I put a phase in there. I can just call this thing alpha plus beta, right? And in fact, if I compute this concretely, I will get the phase. I'll get 0 plus e to the I alpha plus beta when I apply this multiplication. If I conjugate it, I get the negative, of course. And 0 is just the unit. So this thing really does define the abelian group structure for any of my colors. We call this the phase group structure. In this case, the white phase group structure. Now, suppose I want to take some point beta and send it to alpha plus beta. Well, the way I actually conduct this phase rotation is I just multiply on the left or the right with alpha, right? So this thing is called a phase map. So one thing that's you should notice about spiders is that they're totally symmetric in their inputs and their output legs. Right? We just define them that way. All the input and output legs have to be the same, so they're totally commutative. So it doesn't really matter which leg we hook this phase state onto. We could even make a phase effect and hook it onto one of those top legs. It doesn't matter. An immediate consequence of that is if I take one of these phase maps and I apply it to one leg, I could just as well apply it to some other leg. Again, it doesn't make any difference. So we simplify the notation by just having the spiders eat the phases and just write them right on the spider. So this thing simultaneously generalizes the phase points, the phase maps, all that phase too. And in fact, we get a generalized spider rule. So the rule that Bob talked about in his talk and that Chris proved was that if I have any connected diagram of these spiders, they fuse into a single diagram. So if we combine that fact with the fact that these things act as the phase group, they sum these phases up, then if I have any connected diagram of spiders with phases on it, they'll all fuse together and all the phases just get added together. Yeah?
Does it work for more than 2 dimensions? Because if you have for example dimension 3, this phase changes between one set of bases and another that is usually based or whatever. They won't have a simple phase. They will have more parameters that won't add simply like this.
Will they not add simply? I mean, so you'll have multiple parameters.
If you have, for example, 3-dimensional filter space and then cutrix, and then you will have, I think it's how many? Like
you'll have two phases.
Two
yeah.
Usually, no, because you have 3 for 2 dimensions for cubics.
So this doesn't really
I
have.
think you have 8.
This doesn't really have to do with. Well, maybe we should talk about it a bit later.
Yeah. Okay.
So, but yeah, this does work for any dimension. But in higher dimensions, you take lists of phases that add together rather than just single phases. Any other questions about the fusion? Yeah?
So the one on the right hand side looks like global phase change, and if you apply phase on only one leg, like change of one relative phase of one subsystem, and that's the same, or how does this work?
So you should think of a spider like this that's got one big phase on it. This thing isn't a global phase, it's again a relative phase, but it'll be, say, a bunch of zeros, and then the relative phase is here. So still we ignore global phases, but these things really capture a relative phase with respect to that basis.
Yeah, in higher dimension, you just have more terms.
Yeah, that's right. So I have alpha 1, 1, alpha 2, 2, and on. So if we take a complementary pair of basis states, or a complementary pair of bases, then as I already mentioned, the basis states of one of the colors, of white say, are unbiased with respect to the other color. So we could also write these things as phase states. So any unbiased state can be written as one of these phase states. So in 2D, we can just write this as, we can write the 0 state as a gray 0 phase, and we can write the 1 state as a gray pi. Right? So that's a gray 0 is this one, the I 0, 1, right? So that's just plus. Minus, right? So it just gives us a way of writing those basis states in terms of phases of the other. So since the gray dot gives us a way that we can multiply phases, it gives us this phase group structure. It also gives us a structure on the basis states of white. Right? But this doesn't necessarily need to be a group structure. And in fact, for general unbiased bases, if I just take two arbitrary basis elements and I multiply them with the other one, then there's no reason I would expect to get a third basis element back. Right? And that's one of the reasons that arbitrary modes are so hard to classify, because they don't have these kinds of nice structures. But in the example I gave you, this is the case. Right? So if I take 0 plus 0, I get 0, 0 pi is pi, pi 0 is pi, and pi pi is 0. Right? So I always get another basis state back. So this is a very special kind of complementary pair of observables. And before I give you the full definition, something you should notice is that the gray dot here is leading kind of a double life. On the one hand, we can look at, well, I can just look at these equations. I can take the singled form of those equations, and I can see what this thing is doing. This gray dot on my classical data is actually just taking a Z2 sum of these things. Right? So that should have been a 1. Anyway, so the gray dot is just acting as a classical map. It's actually XOR. It's a classical map from 2 bits to 1 bit. Right? In general, it's a classical group multiplication operation. On the other hand, it's a quantum operation that goes from 2 phase states to another phase state. Right? And these 2 roles that gray plays are related to each other. So via this white preparation. So if I take 2 white basis states and I XOR them, and then I prepare it as a quantum state, that's the same thing as if I prepare 2 quantum states and then I do this sort of quantum XOR operation on them. Right? So we get this equation, and also if I take my unit and prepare it, I'll get a gray unit. So you get some kind of interesting equation come out of this group structure. And we take these interesting equations to be our definition for these very special kinds of complementary observables. We call a pair of observables, or a pair of spiders, strongly complementary if these 3 equations are satisfied. So this one just says that the gray dot is a stochastic map, which it is. It's a deterministic function XOR on your bits, right? And then these 2 are the ones that I explained on the other slide. Unfolding this stuff, you actually get something that some people here might find familiar. You see that strongly complementary observables are exactly bialgebras. So if you know this sort of stuff, these are the 3 equations that characterize a bialgebra. You have to get used to this double notation to see that, especially that first one, really is the unfolding of that first equation. Yeah. So strongly complementary means bialgebras. So first, because we gave it a kind of leading name, we should prove that these strongly complementary things are in fact always complementary. And that's not hard to do, it's just a graphical proof. Right? So we're going to assume strong complementarity, and we're going to try to prove this complementarity equation. Right? So we unfold, and then here we've just done some deformation, and we've put a couple of identities on here. I think Bob implied it, but maybe not explicitly. All of these spiders with one leg in, one leg out are just equal to the identity. Right? So that captures the unit law as a sort of, if I fuse a dot in there, get the identity. Right? So here, we just do some deformation, introduce 2 identities here, and then we sort of pull these spiders apart, and then we get something that looks like one side of this bialgebra equation. We use it, and then we use the two copy equations, which breaks up our diagram, and then we just get rid of this extra gunk, and then we get the proof. Proof takes a little bit longer if you're being really careful about scalars and that sort of stuff, but it follows quite easily. Unlike most, strongly complementary observables are really easy to classify. For one thing, there's no question about how big a maximal set of strongly complementary observables is. It's always 2. If we have 2 strongly complementary observables, then there's no other observable which is pairwise complementary to both of them. Right? So we always talk about pairs of these. And these pairs are totally classified in all dimensions. And they are classified by finite abelian groups. So a pair of strongly complementary observables is in one-to-one correspondence with an abelian group of order that dimension. And the theorem actually sounds a lot more impressive than the proof. This thing acts as a group operation on an entire basis. So we know what it does on a basis. That totally characterizes this dot, right? And then once that dot is totally characterized, that totally characterizes this basis. So as soon as I fix one basis and I fix an abelian group, then I have the other basis for free. So it totally classifies. And conversely, for any group, I can construct such a pair, which we'll witness that. So earlier I was trying to give some sort of pseudo-operational interpretation for this equation. I mean, for the complementarity equation, it's very easy. You know, we can talk about preparations and measurements, and we get known data flow, and we can talk about experiments which witness it and stuff. But this one's a bit weirder. And the thing that makes it a bit harder to explain is that's not really, well, it's not causal, for one thing. That doesn't satisfy the causality postulate. So even though this thing is valid as a quantum map, it's a CP map, but it's not trace preserving. So we can't really think of it as something that happens, right? It's something that it could be, you know, post-selected or something like that. Yeah. So here's the. In fact, if I trace out this output, I get something which is kind of like decoherence turned sideways, which definitely isn't the throwing things away, right? But that's because it's both pure and it throws stuff away, right? So XOR is not an injective or a bijective map, right? It's not reversible. We threw away some information, and yet this thing is a pure map, so we had to do some post-selection somewhere, right? However, we can get a good quantum map. We can build a good quantum map out of this, and we do something which is basically a kind of standard trick from all these quantum computing type algorithms and stuff, which is just we copy some of the input. So here's a white spider, we've copied some of the input and hung on to it, right? And then now this thing is everything you want, right? So for one thing, whenever white and gray are unbiased, then this map is causal, right? Because we get these two sort of decoherence looking things, and then this wire falls off, and then we just get two discards there, right? And since it's pure and causal, then it's unitary. In the ZX example, this thing is actually a C0 gate, and you can see why. If I put in two white basis vectors, then this one gets copied by the white dot, right? And then this thing acts on X or acts on white as XOR, right? So this thing is just C0. So you're already starting to see that we're using these spiders to start to build something which we're going to at least be able to build quantum circuits out of. And actually lots and lots more. So we can build C0 gates. We can also build any single qubit unitary just via the Euler decomposition. So these gray phases are rotating around the x-axis, and these white phases are rotating around the z-axis. So I can construct any single cubic unitary as 3 rotations like that. So this follows very easily from Nielsen-Schwang type argument that these two maps are enough to build any quantum circuit. You just build a C naught, we build single cubic unitaries, and that's really what we need. So an immediate corollary of that is that this thing, and this thing are enough to build any quantum map. And the way that works is we can just take our arbitrary quantum map and we can do dilation, and then that handles these things, and we just have a pure thing in the middle. And then we can construct any pure thing using this and this. Because in particular we can do post-selections and syllogisms and that sort of stuff. Alright, so we have a language that's universal when all of our input and our output wires are qubits. So we have enough generators to build any quantum map. But the question is, can we reason about those quantum maps once we have them? In other words, do we have enough relations, so equations between diagrams, to prove the 2 quantum maps are equal? So we already have a few. So you might start to be tempted to think that maybe we have enough. But there's things that we can't prove yet. So for instance, this one is true. I'll just give that as proof by authority, but it's I don't have much authority. But that one's true, but we can't prove it. In fact, there are models of all the rules I gave you so far in which that equation doesn't hold. So it's not provable from the equations we have already. And actually, whether a finite complete set of rules for the full language, so for arbitrary phases, exists is still an open problem. My prediction is no, that no such thing exists, that we need to do something a bit clever. We need to talk about families of rules rather than just individual sort of concrete rules like that. But we can make the question a bit easier by restricting to the Clifford maps. So Clifford maps consist of any map that we can build using that guy, and that guy, right? And that's already quite a bit. I mean, if we restrict just to the unitary Clifford maps, we have all the Clifford circuits, right? So we have the whole classically simulable fragment of quantum circuits just from these guys. And we very nearly have a complete set of equations. But the thing that's missing is some extra information about the Bloch sphere and how it behaves under certain rotations, right? So one thing, I don't really know what to call this, but this must be a pretty standard fact about spherical geometry, which is that if I rotate, say, I guess this is clockwise or anti-clockwise, depending on whether I'm looking up or down at it. But anyway, if I rotate by alpha, and then I flip the whole thing upside down, I can just as easily flip the whole thing upside down and rotate by minus alpha. Right? So that gives you a hint that we're working with a sphere, right, this equation. And the second concerns the Hadamard gate. So it concerns our color changer, the thing that interchanges the 2 bases. Now this thing is also a rotation on the Bloch sphere, right? It's like, well, you can, I'm sure a lot of you have worked this out at some point, but it's these sequence of 3 rotations. So if we include the fact that the Hadamard, which is defined as this rotation, is in fact a color changer, then that adds a new rule to our equation, or to our system. And that's in fact everything we need to define the ZX calculus, right? So these 2 spider fusion rules, the strong complementarity rule, with an extra one accounting for the fact that this is also a white basis vector, right? So it gets copied by the white copy. And these Bloch sphere rules, right? So we have, what, 1, 2, 3, 4, 5, 6, 7. You could either call that a rule or a definition as you like, right? So now we have these 8 rules, And this defines the ZX calculus, which is our kind of, at least my bread and butter for the last couple of years. And the ZX calculus is actually complete for the Clifford fragment. Right, so this is enough if I have two Clifford maps to prove that one is equal to the other. There's hopefully a nicer proof of this, which is something that I'm digging for at the moment. But one proof makes use of this graph theoretic trick called local complementation, which we borrow from NDQC. And on Wednesday I'll talk a bit more about how the ZX calculus and NDQC are really closely related to each other. So we can sort of steal tricks from them or send tricks back. So anyway, the proof of this is a trick out of NDQC. So ZX is complete for this classically simulable fragment. We can prove that it's incomplete for arbitrary phases. And an actual formal proof of this was given by Vladimir, who's there recently, and another student called Christian Sternberg. What? What? Incompleteness. Oh, yeah, Miriam proof completeness. I think she's also here as well, probably. Yep, there she is, my new camera. So, yeah, she proved this completeness theorem. I didn't mean to say it's just a trick, I didn't see it. It's a very nice paper. And it's also complete for at least one other fragment. This result was also shown by Miriam, I think using a recent paper by Selinger, which proved a similar thing in the circuit context. At least if we restrict to single qubits, which is a bit boring, but at least if we restrict to this single qubit case, we can actually get completeness if we go from pion 2 to pion 4 phase maps. So this is like including T-gates. So this is the approximate universal fragment of the language. But it's totally unknown whether the n-qubit approximate universal case is complete or not. So that's kind of the note I wanted to finish on. So what I did was built up the ZX calculus, which, as I said, is this kind of Swiss Army knife for working with qubits. And then along the way, we came across these two important relationships between pairs of measurements. So we had this complementarity rule and this strong complementarity rule. I mean, lots and lots of people have studied. This is a bit less well understood, I guess, but somehow it sits in between complementarity and something like two bases being canonically conjugate or something. So whenever one basis is, say, the Fourier transform of another one, you get one of these kind of strong complementarity things. So it seems to play an important role, and actually I'll talk on Wednesday about how you can use it to actually construct some non-locality arguments and things like that. Yeah, that's what I'm saying there, point 4. So you could say that most of today was kind of about tooling, about building up the ZX, and next time I'll talk about actually using it. So there's a very nice way that you can talk about several quantum algorithms using this language, and it becomes very intuitive how constructing classical oracles works and why they work and that sort of thing. Also, it seems to be just pretty much built for doing MBQC, because you can do lots of nice things in MBQC. And also talk a bit about security and non-locality. And demonstrate a recently completed and still not debugged tool called Quanto-Derive, which automates working and calculating with the ZX calculus, which is something that me and Vladimir have been working on mostly lately, and can do some pretty cool stuff. So I would recommend you, if you're going to come, in the second half of my talk, and don't want to see the boring stuff in the front, I would recommend you at least see And that's it for now, so thanks.